Yo, one sec.
What are you reviewing?
No, I'm just gonna
Oh,
just go through like an exam because I didn't have like for calc I made like a whole like slideshow, but I didn't really have time for physics. Hold on. What is this? Alright, this is also like the 2015 test if you want to like follow along, or if you know. Just gonna wait a little.
but we can bring graphing calculators, right? Physics.
Yeah. Hold on. I'll wait just a little longer. Wait, does the stream work, Addison?
The Discord stream or the Twitch stream?
Check the Twitch stream. I don't know if it works.
I'll check it. Oh, it looks like it works.
Alright. Okay, I'll just start right now. Okay, so for this first question, in which of the following situations is the kinetic energy of the object decreasing? Basically, kinetic energy is a scalar quantity, so you're basically looking for when the speed is decreasing. So a sphere is dropped from a building, the kinetic energy is increasing because the velocity is like getting more and more negative. A satellite is moving in a circular orbit around Earth. No, because it's like a constant. Wait, hold on. No, it's like because the velocity, like the magnitude of the velocity isn't changing, but only the direction is changing. A baseball is headed upward after being thrown at an angle. Yeah, that's true because the gravity is like slowing the baseball down, so the speed is decreasing. This one we can skip because it's like electricity. Number 3, 2 kilogram object traveling at 5 meters per second on a frictionless surface collides head-on and sticks with a 3 kilogram object initially at rest, which if flying correctly identifies the change in total kinetic energy and speed after the collision. So since it's an inelastic collision, the kinetic energy is going to decrease, so we can eliminate those two. And then for the speed, we can just solve momentum initial equals momentum final. So the initial momentum is 2 times 5. The final momentum is 2 plus 3 times v final. V final is equal to 10 divided by 5, which is 2. So C is the answer. Whoops. A stone of mass m is thrown upward at a 30-degree angle. At the instant the stone reaches its highest point, why is the stone neither gaining or losing speed? So the acceleration at that instant is 0. That's not true because gravity, the acceleration is negative 9.8. The net force at that instant has a magnitude of mg. Yeah, that's true, but that doesn't really explain why the stone is neither gaining or losing speed, because that's the net force like throughout the entire trajectory. Because the angle between the stone's velocity and net force is 90 degrees. That's true. And since the net force is perpendicular to the velocity vector, that means that acceleration is perpendicular. So only the direction of velocity is changing at that instant and not the actual magnitude. And then because the stone follows a parabolic trajectory and the peak of the trajectory is where the parabola has 0 slope. But that doesn't really explain why the stone is neither gaining or losing speed, because that just shows that like the velocity at that point is 0. So C is the best explanation for why the stone is neither gaining or losing speed. Okay. A small car is rolling freely on an inclined ramp with constant acceleration 0.5 meters per second in the negative x direction, which at time t equals 0, the cart has a velocity of 2 meters per second in the positive direction. If the cart never leaves the ramp, which of the following statements correctly describes the motion of the cart at time t is greater than 5? So we can say that the acceleration is negative 0.5 meters per second, and initial velocity is 2 meters per second. And let's just solve for at t equals 5, and t is equal to 5. So let's just solve for final velocity. So we can use v final is equal to v initial plus at. So that's 2 plus negative 0.55. So that's 2 minus 2.5, which is negative 0.5. So the velocity is negative. So that means it's moving in the negative x direction. And acceleration is also in the negative x direction. So since velocity and acceleration are in the same direction, it's speeding up in the negative x direction. So 5 is D. 7, a box of mass m is on a rough inclined plane that is at an angle with theta with the horizontal. A force of magnitude F at an angle gamma, I think, with the plane is exerted on the block as shown above. As the block moves up the plane, there is a frictional force between the box and the plane of magnitude F. What is the magnitude of the net force? So let's just draw a free body diagram. So there is F pointing there, there's mg, and then there's friction. So the net force should be in this direction. So let's just make our components in that direction. So there's a component here, F cosine that. There's F here, and then also, honestly, you should just memorize this whenever you see a plane. The components that's parallel to the plane is mg sine theta, and the component that's perpendicular to the plane is mg cosine theta. So the net force is F cosine gamma minus mg sine theta minus F. So C is the answer. Sorry, that was kind of messy. An object's velocity as a function of time is given in the graph above. Which of the following statements is true about the motion of the object? The object is not moving from t equals 4 to t equals 10. So you can see that the velocity, the line is straight here on this graph, but it's a velocity time graph. So that just means that it's moving at a constant velocity. So it is moving. The object's initial and final positions are the same. So that means that the displacement is 0. And in order to calculate that, we just have to find the area under the curve. So let's see. These are two trapezoids, 14 and 6. This is 22, or wait, no, that's not 22. This is 22, and this is 18. 4. Okay. So the area of this first one is 14 plus 6 times 10 divided by 2, which is 100. The area of the bottom one is 22 plus 18 times 5 divided by 2, which is also 100. So the net area under the curve is 0. So that is true, that the displacement is 0. So the initial and final positions are the same. So an object is slowing down from 14 to 16. 14 to 16 is right here. No, it's not, because the acceleration is negative, because the slope is negative, and also the velocity is negative, so it's speeding up. And then average acceleration from 0 to 4 is different from 34 to 36. That's not true, because from 0 to 4, the average acceleration is 10 over 4. Whoops. And then from 34 to 36, it's 5 over 2. And those are the same. And then these are circuit problems, so we can skip those. A block of mass m of mass 10 kilograms moves from position A to position B. The speed of the block is 10 meters per second at A and 4 meters per second at B. The work done by friction on the block as it moves from A to B is most nearly. So this is an energy problem. So initially there's some kinetic energy, and then at the end there's some gravitational potential energy, and then there's also some kinetic energy because it's moving at B, and then there's going to be, and plus the work done by friction. So what's initial kinetic energy? That's 1/2 10 squared. What is the final potential energy? Well, you can see the height is 2 meters. Potential energy is mgh, so that is 10 2. Plus final kinetic energy, that's 1/2 10 4 squared. And then plus work done by friction. So if you solve for work done by friction, let me just plug it in real quick. You get 220 joules, or negative 220 joules. Wait, hold on. Oh yeah, because it's negative. Because, well, you get 220 joules, but the work done, I mean, technically I should have put it in on this side because it's like negative work. But yeah, you can just change it to negative once you calculate it. This is a wave problem, so we can skip it. Number 13, a ladder at rest is leaning against a wall at an angle. Which of the following forces must have the same magnitude as the frictional force exerted on the ladder by the floor. So the ladder is like this. Okay, so the frictional force is this way, so that it stops the ladder from sliding. So, and the ladder is at rest, so there must be a horizontal force that cancels out the frictional force. So the force of gravity on the ladder is downwards. That's not it. The frictional force exerted by the ladder on the wall, that is upwards. That's not it. Or, well, both of these forces are vertical, so we can eliminate them. The normal force exerted on the ladder by the wall, that is horizontal, perpendicular to the wall. So that should be the answer. And then the normal force... Oh, shoot, wait. Sorry. Wrong one. The normal force exerted on the ladder by the floor, that's right here. That's vertical, that's not it. The normal force exerted on the ladder by the wall, that is perpendicular to the wall and it's horizontal, so that is the answer. Some students wanted to calculate the work done by friction as an object with unknown mass moves along a straight line on a rough horizontal surface. They have a force probe, a meter stick, and a stopwatch, which with flying will allow students to take measurements to calculate the work done by friction. So to calculate the work done by friction, you probably need to know like force and distance. Work is equal to force times distance. So that's probably the main things you want to know. So we can eliminate A and B because they say force and time. So pulling the block at an unknown constant acceleration with the force probe for a measured distance, or pulling the block at an unknown constant speed with the force probe for a measured distance. So if you pull a block with an unknown constant speed, that means that the net force is 0, and because the acceleration is 0. So that means that the reading that you see on your force probe will be the force of friction, and then you could just multiply it by the measured distance. So that would be the best way to calculate the work done by friction. Okay. A pendulum, number 15. A pendulum consisting of a sphere suspended from a light string is oscillating with a small angle with respect to the vertical. The sphere is then replaced with a new sphere of the same size but greater density and ascend to oscillation with the same angle. How do the period, maximum kinetic energy, and maximum acceleration of the new pendulum compare to those of the original pendulum? So this new sphere has the same size but greater density. So that's same size, so like same volume but greater density. Density is equal to mass over volume. If it has the same volume but greater density, that means it has a greater mass. So this new sphere has a greater mass, and it's a pendulum. So period of a pendulum is 2 pi square root of length over g. So it's independent of mass. So period should stay the same. Maximum kinetic energy should increase because since the sphere is more massive, it'll have a greater initial gravitational potential energy, and then therefore it'll have a greater maximum kinetic energy. So that's D. And then maximum acceleration should stay the same because the acceleration is caused by gravity, and the acceleration due to gravity won't like change because you change the mass. It's always constant. Yeah. Planet X has twice Earth's mass and 3 times Earth's radius. The magnitude of the gravitational field near Planet X's surface is most nearly. So the magnitude of the gravitational field is basically little g. So little g is equal to big G m over r squared. And the way I got that is basically if you set mg equal to gm, over r squared. You can cancel out the small m's and get that. Because these are basically, these are both equations for the force of gravity, except that this equation is used when you're like dealing with like different distances and stuff, or different masses. So if it's 3 times or twice Earth's mass and 3 times Earth's radius, g is equal to 2gm over 9r squared. So it's 2/9 g on Earth. And g on Earth, let's just say it's 10. So 2/9 times 10 is about 2 point something. Yeah, it's like 2 point something. But basically, the answer is 2. A force F is exerted on a 5 kilogram block to move it across a rough surface, as shown above. The magnitude of the force is initially 5 newtons, and the block moves at a constant velocity. While the block is moving, the force is instantaneously increased to 12 newtons. How much kinetic energy does the block now gain as it moves a distance of 2 meters? So the work energy theorem states that the work done is equal to the change in kinetic energy. So how much work is done on this? So initially it's just being pushed with a force of 5 newtons, but it's increased to 12 newtons. So a net force of 7 newtons is exerted over a distance of 2 meters. So 14 joules of kinetic energy should be gained. Okay. These 18 and 19 are wave problems, so we'll skip those. A system consists of a disc rotating on a frictionless axle on a piece of clay moving toward it, as shown in the figure above. The outside edge of the disc is moving at a linear speed v, and the clay is moving at a speed v over 2. The clay sticks to the outside edge of the disc. How does the angular momentum of the system after the clay sticks compared to the angular momentum of the system before the clay sticks? So the system consists of the disc and the clay. So angular momentum should be conserved. So A is the same because there is no external torque acting on the system. A disk of known radius and rotational inertia can rotate without friction in a horizontal plane around its fixed central axis. The disk has a cord of negligible mass wrapped around its edge. The disk is initially at rest and the cord can be pulled to make the disk rotate. Which of the following procedures would best determine the relationship between applied torque and change in angular momentum? So we want to know the relationship between torque and change in angular momentum. So let's see. So part B looks wrong because applied torque, so we want to know the relationship between applied torque and angular momentum. So what we should do is do different values of torque and see how it changes the angular momentum. But in B and C, they're both exerting a force of 15 newtons throughout the whole experiment, but they're just changing the time intervals, which it will change the angular momentum, but those are better for exploring the relationship between the time at which a torque is applied and angular momentum. But we want to know the relationship between the torque and the angular momentum. So those are eliminated. And then for 5 forces of different magnitude, pulling on a cord for 5 seconds and then measuring the final angular velocity. That is a good way because you're changing the torques and you're applying them for the same amount of time, and then you're seeing how it affects the change in angular velocity, which angular velocity is I time, or angular momentum is rotational inertia times angular velocity. And then A is just, it's just not really, because yeah, the torques are different, and then you're seeing how it affects the angular angular velocity, but it just doesn't really like make sense. Like you just wouldn't do that, because it's best to like keep time constant if you're just looking to explore the relationship between torque and angular velocity. 22 is, we can skip. Each of the figures above shows a tractor attached to an object. The tractor exerts the same constant force F on each object. Which of the following statements is true about an object and the relative magnitude of the force exerted by the object on the tractor? So the tractor is pulling each of these with the same force, and Newton's third law says that means the objects should pull back on the tractor with the same force. So D is the answer. A planet is in an elliptical orbit around a star, as shown above. Which of the following best represents the mechanical energy of the planet and the star-planet system as a function of time? So the star-planet system the energy should stay constant, so we can eliminate B and D. But the planet energy should change, because it's
for the truck and tractor problem. Why is it not A?
Truck and tractor. The magnitude of the force exerted by the truck on the tractor is greatest because the resulting motion is in the direction opposite of the tractor's pull. Well, let's see. So it's probably, it exerts the same force, but probably because the truck is more massive. I don't know. Well, basically, the magnitude of the force of all of them should be the same. Like that's basically like.
Oh wait, no, it makes sense. It makes sense. It's probably because the truck is heavier, so the normal. Yeah. Never mind.
Yeah. So for this one, the energy of the planet should be changing because it has kinetic energy, but as it moves like closer to the star, it should get more kinetic energy, and then the kinetic energy decreases. So it's not constant, so it's not A. So C is the answer. A cart of known mass moves with known speed along a level frictionless track, as shown in the figure above. The cart hits a force sensor and rebounds. The force sensor measures the force exerted on the cart as a function of time and as a function of position. Which of the two graphs can be used to determine the car's speed? So force position graphs, we can determine the work done, and work done tells us the change in kinetic energy. Force times times graphs can tell us the change in momentum. So change in kinetic energy and change in momentum, they can both be used to find the velocity after the collision. So they both can be used. Because we know the initial speed and we know the mass. The figure above represents the orbits of two planets of equal mass that orbit their star in the counterclockwise direction as a double planet system. From the point of view of an observer on either planet, The planet appears to orbit each other while also orbiting the star. The dots on the orbits represent the position of the planets at time t0, and x is the position of their center of mass at that time. Which of the following arrows best represents the acceleration of the center mass of the double planet system when it is at point x? So at point x, the force on the center of mass is the force of gravity, which is directed towards the star. So the acceleration should be in that direction. So A is the best. Because B, it's like a little too like horizontal or whatever. Two identical blocks are connected to the opposite ends of a compressed spring. The blocks initially slide together on a frictionless surface with velocity v to the right. Okay, so they're connected. So they initially go v. The spring is then released, and at some instant later, the left block is moving at v over 2 to the left, and the other block is moving to the right. So we have this one going v over 2, and this one going to the right. What is the speed of the center mass at that instant? So if there's no external force on the system, then the velocity of the center of mass stays the same. So it's v. Because initially the whole system was moving at v, so we can assume that the center of mass was moving at v, and when they separate, there's no external force acted on the system. It was just like an internal force, but so the velocity of the center of mass should stay constant, so it's v. Okay. A person holds a book at rest a few feet above a table. The person then lowers the book at a slow, constant speed and places it on the table. Which of the following accurately describes the change in total mechanical energy of the Earth book system? So if the person didn't like lower the book, it would just fall down at an acceleration of g. But instead, he lowered it with his hand, so it fell down at a constant speed. So he did negative work on the book. So the energy decreases d. The person does negative work on the book by exerting a force on the book in the direction opposite to its displacement. A system consists of two spheres of mass m and 2m connected by a rod of negligible mass. The system is held at its center of mass with the rod horizontal and released from rest near the Earth's surface. So the graph above shows the rate of change of linear momentum of the sphere of mass m as a function of time. What is the linear momentum of the two-sphere system at time t equals 3? So this is change. On the y-axis, you have change in linear momentum. And then you have delta t. So the area under this curve is, dp over delta t. That's on the y-axis. That's the rate of change of the linear momentum. So the area under the curve would give you change in momentum. And I think all of you guys are in calculus, so it's basically like the rate of change, and then you integrate it, and then that gives you just the change. So the change in momentum of the sphere of mass m is 5 times 3, which is 15. So, but that's just this of sphere of mass m. So for the two-sphere system, the mass is 3m. So this is delta P equals mv equals 15. So delta P, I'll say delta P2 is equal to 3m v, which would be 45. C. Which of the following best explains why the system does not rotate around its center of mass as it falls? The Earth exerts the same gravitational force on both spheres, causing them to accelerate at the same rate. No, it doesn't. It exerts a greater force on the larger sphere because the thing, what's it called? The larger sphere has more mass, and the acceleration due to gravity is going to be constant. So the force of gravity is greater on the larger mass. And then, so the Earth exerts the same gravitational force on both spheres, generating torques that cancel out. No, it does not exert the same gravitational force on both spheres. The Earth exerts a larger gravitational force on a sphere of mass 2m. That is true. But that sphere is closer to the center of mass, and the torques cancel out. Yeah, that's true. Because the center of mass, since 2m is more massive, it's around here. So if you have a larger force, but a shorter distance, that's going to be the same torque as a longer distance, but a smaller force. So that's the answer. So for part D, the Earth exerts a larger gravitational force on the sphere of mass 2m, but that sphere has more inertia and the torques cancel out. The sphere having more inertia doesn't really explain why the torques cancel out. So I think that's just the only reason why D wouldn't be right. Even though it's true that the sphere has more inertia. A person is running on a track. Which of the following forces propels the runner forward? So, the force that propels the runner forward should be parallel to the ground, because, see, that's my running person, because he's going this way. So a normal force exerted by the ground on the person, that's a vertical force, not that. Same with this. The force of friction exerted by the ground on the person, that's right. And it's not D, because the force of friction exerted by the person on the ground would be this way. But the ground is exerting a force on the person. That's what's causing the runner to go forward. Okay, one sec. All right. In a one-dimensional, perfectly elastic collision, an object of mass m is traveling with a speed of v0 in the positive x direction when it strikes an object with mass 3m that is at rest. What are the object's velocities following the collisions? So I think in this problem, I'll do it two ways. In this problem, I think it's just easiest to check the answer choices because we know that momentum is conserved. So m1 v1 is equal to, or v0 is equal to m1 v1 plus 3m v2, and 1/2 m1 v0 squared is equal to 1/2 m1 v1 squared plus 3/2 m v2 squared. So if you cancel out the m's, you get v0 is equal to v1 plus 3v2, and v0 squared is equal to v1 squared plus 3v2 squared. Okay, so v0, so So let's just check them first. So, and this is v1 and this is v2. So 0 and v0 over 3. v0 is equal to 0 plus 3 v0 over 3. Yeah, that works. v0 over 4 and v0 over 2. v0 over 4 plus 3 v0 over 2. No, that's not true. Those are not equal. What about v0 over 2 for both of them? No, that's not true. What about for this one, negative v0 over 2 and then v0 over 2? Negative v0 over 2 plus 3 v0 over 2. That is true. Okay, so now that we eliminated some answers by just using conservation of momentum, let's test conservation of energy, because since it's an elastic collision. So 1/2, so it was v0 squared is equal to v1 squared plus 3 v2 squared. So let's test A. 0 plus 3 v0 squared over 9. That's not true. So it's D, but let's just check it real quick. It's equal to v0 squared over 4 plus 3 v0 squared over 4. That is true. So D is the answer. All right, one sec. Okay. A student conducts an experiment to determine the relationship between applied torque and change in angular velocity. The student uses the apparatus shown in the figure above. Blocks of various mass. The blocks are released from rest, exerting different torques. For each block, the time fall t and the final angular velocity are measured. There is considerable friction between the disc and the axle, which of the following represents a plot that can be obtained. So applied torque and final angular velocity over time. Initial angular velocity was 0, so this is just angular acceleration. So applied torque and angular acceleration have a positive direct relationship. So it can't be, what's it called? D. So there is considerable friction. So that means that even if you apply some torque, it won't move until you apply enough torque to overcome the friction. So A is the answer. It's not C because it starts at the origin. So that means, if you apply, say like this amount of torque, it just goes like that. But in reality, you need to apply enough torque to overcome friction in order to start rotating the thing. And it's not B because this shows that it's like the wrong way. So it shows that, if you apply this amount of torque, you'll get a higher angular acceleration. Like, it just doesn't really make sense. So A is the answer. An athlete with mass M running at speed V grabs a light rope that hangs from a ceiling of height H and swings to a maximum height of H1. In another room with a lower ceiling of H, 1/2 H, a second athlete with mass 2M running at the same speed grabs a light rope hanging from the ceiling and swings to a maximum height of H2. How do the maximum heights compare? So this is conservation of energy. So they all have initial kinetic energy, and then when they reach the max height, it's going to be potential energy. So 1/2 mv initial squared is equal to mgh. So h is equal to, masses cancel out, initial velocity squared over 2g. So in this one, its mass is m and velocity is v, so we'll just leave it like that. In this one, his mass is doubled, but his velocity is kept the same. So height, the max height doesn't depend on the mass though. It only depends on the velocity and the acceleration due to gravity. So since their velocities are the same, they reach the same height. And the length of the rope doesn't matter. Yeah, it just doesn't. Okay.
I gotta go, but thanks, Aaron.
All right, see it.
Bye.
35. Does at least one of these ships have its, or two identical spaceships are traveling in deep space far from any planets or stars. The ships travel in the same direction with the slower one directly behind the faster one. The ships are connected by a cable attached to a spool so that the part of the cable outside the ships can be made longer or shorter as needed. The cable is used to bring the ships to the same speed for a transfer of cargo. Okay, so does at least one of these ships have its engine on during the time interval shown below? Okay, so they have the same mass. So let's see how their momentum, how the momentum changes. So the initial momentum is m times 8010 plus m times 79090. And then the final momentum is when they have the same speed. So if you add these, you can see that momentum increases because this is the initial momentum, and then the final momentum is this. So momentum increases, so that means that there's an external force on the system, and so B. And an engine is, or a fuel propeller, an engine, whatever, that is an external force. Just remember that. Which of the following graphs best represents the net force exerted on the two-ship system? Okay, so you can see that the slope of the velocity time graphs for both of these are pretty constant. Are pretty constant. So that means that the acceleration is pretty constant. So that means the net force should be pretty constant. So it's not A or B. And there is a change in momentum. So there should be an area under the curve. So it's not D. So C is the answer. These are all other stuff, so we can skip these. And that's it for this test. So I'm just gonna, I think that's all. Unless you guys want to do more, but doesn't matter.
You got FRQ stuff? Just maybe we can do one or two.
Sure. Yeah, we could do that. One sec. Okay. Okay, so a cart A of mass m is released from rest at height 2h, making an angle 2 theta with the horizontal as shown above. Cart B has mass 2m and is released at height h on a ramp making an angle theta with the horizontal. The carts roll towards each other, have a head-on collision, and stick together. and there's no friction, and there's no like rotational energy from the wheels. So in order to determine, so we need to apply conservation of energy and conservation of momentum. So let's apply conservation of energy in order to solve for the velocities when they collide. So for cart A, it's it's capital mg2h equals 1/2 mv squared. So v is equal to 4gh square root. And then for cart B, it is 2mgh equals 1/2 mv squared. So v is equal to square root of 4gh. So they have the same velocities when they collide, and they stick together. So initial velocity, let's just take this as positive direction. So m square root of 4gh minus 2m square root of 4gh equals, they stick together, so their combined mass is 3m v. So this is negative m square root of 4gh over 3m equals v. So velocity is negative. So, and we said that right word is positive, so that means the left word is negative. It moves to the left. Okay, one sec. Okay. So B. Consider the time interval from when the two carts are released until just after they collide. So for the system consisting of the two carts and the Earth, does the mechanical energy increase, decrease, or remain the same? It remains the same because there's no like external force. No external force. Okay, so for the system consisting of only the two carts, indicate whether the total mechanical energy increases, decreases, or remain the same. Well, initially they're at rest. Initially they're at rest on top of their like ramps. So the carts themselves have no mechanical energy, but at the end they're moving to the left. So at the end they have kinetic energy. So it goes from 0 to kinetic energy. So that's an increase. Okay. I think that's that. Okay, so a car is stopped at a traffic light. The light turns green, and at time t equals 0, the car starts moving and travels with constant acceleration. At that instant, a truck traveling at constant speed vt is alongside a car, with the front of each vehicle at position x equals 0 as shown above. The truck passes the car, but the car later catches up to the truck in front of the house, such that at time td, the front of each vehicle is at position x equals d. So, sketch velocity versus time graphs. Okay, so for the car, okay, let's just say TD is right here. Actually, no. So it travels with constant acceleration. So for velocity time graph, the slope is constant and positive. So it's like that. And let's say this is TD. So, and this is, never mind, that's not. Okay, so the constant velocity of the truck should be right here. About, hold on. No, I drew this bad. Wait. Okay, it should be right here. Wait, no. Hold on, sorry. Yeah, move that up a little bit. Should be right here. And then TD. So basically, they end up at the same spot. So their displacement in this is the same. So the area under the curves should be the same. So that's why. And this is the car, truck. This is VT. So the car is moving with a constant acceleration. The truck is moving with a constant velocity. But their areas under the curve should be the same. What, TD? Oh wow, this is long. Okay. Two students are discussing how the speed of the car compares to the speed of the truck when both vehicles are in the front of the house. Student 1 says the distance traveled by the car and the truck is the same, and the time is the same. 1 IB. Hold up one sec. Let me see. Oh yeah, true. It's an inelastic collision, so kinetic energy is lost. So, oh yeah, because it's just after they collide. Okay. So when they're flying down the ramp, there's no energy is lost, but once they collide, they lose energy due to like internal forces and heat and stuff like that. So yeah, Hillary, you're right. Energy decreases. Okay. So student 1 says the distance traveled by the car and the truck is the same and time is the same, so they must have the same speed. Which aspects of his reasoning are correct? He is correct that the distance and time are the same. And then student 2 says, I don't see how that can be. The car catches up to the truck, so the car has to be going faster. And he is correct in saying that the car is going faster. Okay. So derive an expression for acceleration. Express your answer in terms of d and vt. So we know that d and vt is the constant velocity. So vt is equal to d over td. So td is equal to d over vt. So the acceleration of the car, the initial velocity of the car was 0. Delta x was d, t was td. So let's solve for a. We can use delta x equals 1/2 a t squared. So d is equal to 1/2 a, and then t was d over vt. So 1/2 a d squared over vt squared equals d So 2D, wait, hold on, no. Yeah, 2D over, or 2D VT squared over D squared, shoot. 2D VT squared over D squared is equal to A. So a D cancels out, so 2 VT squared over D is the acceleration. Let me just double. Yeah. Determine the time at which the speed of the car is equal to the speed of the velocity of the truck. So if you look at our graph, the graphs intersect at TD over 2 because the displacements should be the same, so that means the area under the curve should be the same. And since truck D is a rectangle and car is a triangle, the car should have a higher, like twice as much velocity at the end. So at TD equals 2, the velocities, the speed of the car is equal to VT of the truck. Three is a wave problem. Let's see. 4 is circuits. Let's do 5. So a toy car coasts along the curved track shown above. The car's initial speed VA when it is at point A at the top of the track, and the car leaves the track at point B with speed VB and angle theta above the horizontal. Assume rotational kinetic energy and frictions is negligible. So assume VA is equal to 0. So after the car leaves the track and reaches the highest point, it will be different than its height at point A. Briefly explain why this is so. So energy is conserved. So initially, there's only potential energy. But at its highest point in its trajectory, right here, it has potential energy and it still has horizontal velocity. So the final energy is potential energy and kinetic energy. So that's basically why it can't go to the same maximum height. The speed of the car when it's at its highest point in its trajectory. So at the highest point in its trajectory, the vertical velocity is 0, but the horizontal velocity stays constant. So, and the initial horizontal velocity is just VB cosine theta. Okay, and then last one. Suppose the car is given an initial push. Determine the speed VA such that the highest point in its trajectory after leaving the track is the same as its highest point at point A. So initially, there's going to be potential energy and kinetic energy. And then final, there's going to be potential energy and kinetic energy. So we want the potential energies to be the same. So that means the kinetic energies have to be the same. So, and the kinetic energy in the final position is the speed at the final position is VB cosine theta. So that means the speed initially should be VB cosine theta as well. Okay.